let's consider our conductor that's spherical with a very non-symmetric hollow chamber. Now, inside this conductor, we're going to put a positive charge Q. And one of the issues that we've said is that the surface of a conductor, the material of the conductor, is an equipotential. Now, this is sometimes confusing to students, because we know if we have a positive Q here, and we'll just indicate that that's positive, then charges will separate in the conductor, and there'll be negative charges in the inner surface of the conductor that will be distributed very non-uniformly because this is a non-symmetric configuration. And what we said was that we had a sigma induced, and that was inner. And because the conductor is symmetric, we have a symmetrically distributed amount of charge. And we know that the total charge on the inner one, if we integrated that, would be minus Q. And so we're having a charge plus Q that's symmetrically distributed along the outside. And let's just indicate that the radius of this is r. Then we know that the potential difference between r and infinity, well, this is just a uniformly distributed sphere, which we've calculated earlier, and that's just our constant k q over r. And again, we'll usually choose our potential difference at infinity to be 0. So now this is the potential not just at the radius r, but this is everywhere in the material of the conductor. And that's the statement that the conductor is an equipotential with this value kq over r. This is often very confusing because we have this inner charge density and we have a uniform outer charge density. We can just write sigma induced outer. This one is uniform. And students find it very confusing that the whole material of the conductor can be an equipotential with these different charges located on the surface. Let's explore that by considering a path from the inner to the outer. We'll call this point A, and this point B is on the outer surface. And we know this is the potential at B on the outer, anywhere on the outer surface. And if we were to calculate the potential difference, recall that the difference between B and A is the integral from A to B of E dot ds. And here, let's just indicate that we're going from A to B. Now, here's the important point. We know that experimentally, the electric field in the material of the conductor is 0. And therefore, this integral is 0. And so you see that the potential difference at every point inside the material of the conductor is the same. And we've calculated it as kq over r. And that's the important point to think about, that the conductor itself is an equipotential. Every point has the same value of the electric potential.